Now with the rate law here, it tells you basically the rate and the rate constant and the concentrations of each reactant and how much the reactant can affect the rate depending on the concentrations. Okay, we have this picture here, but it's only in one given time frame. Like they do some experiment and then they measure the time and they got the rate there. Okay, so this one here is basically the relationship between the rate and the concentration. Now, if I wanted to expand on this, we want to talk about something called the integrated rate law. Okay, so before that, I want to talk about, I guess we'll talk about what half-life is first. All right, you guys good with this? And so I'm going to go and show you some slides here. We're at slide 21. All right, so slide 21 here is talking about half-life. So half-life of a reaction, the symbol is T half. And it basically tells us how long does it take for you to get the concentration of the reactant to go to 50% of its initial value, half of its initial 50%, okay? So in this case here, if you start at 1, after 1 half-life, it's going to be at 0.5. And then you go down to the second half-life, it's going to be 0.25, and then it's going to go to half of 0.25 right there. So what's important here is you probably really hard. It says for a first order reaction, the half-life is constant and independent of the concentration. So I want you guys to focus on first order's half-life. It is independent of the concentration. It's always just going to be a constant time. Like if the first set of time is like, in this case, 100 seconds, the second half-life will be 100 seconds, third, no matter what the concentration is, the half-life stays at 100 seconds here. That's for first order. Okay, and that's something I want you guys to remember because for nuclear decay and all that stuff, like carbon dating stuff, all those things are first order. So we will be doing a lot of first order calculations. And this is important. Just remember, it doesn't depend on the concentration. The half-life is constant. Okay, and I'll show you the formula of the half-life as well for the first order. So that's that. Now I want to show you basically, now here's a chart, a table here. I don't want you to freak out, but we're going to build a table together. Slide 22 here shows you the chart of what we're going to be talking about. So I do want you to memorize this, okay? And I need you to know your integrated rate laws and what the chart looks like, and the units here and what it looks like. So we're going to go ahead and write this out together, okay? You don't have to memorize these two formulas here, and I can show you, if you know the integrated rate law, you don't have to memorize the formulas for these guys. You can actually come up with it on your own. I'll show you an example, okay? So let's go ahead and work on the integrated rate law. We'll do zero order first. So here's what I want you to know. So why do the integrated rate law? When you integrate the rate law, you get another factor here. You can actually tell exactly at what time is what the concentration will fall to. You don't only just know the rate and the concentration, you can actually predict how the rate will change. I mean, not how the rate will change, how the concentration will change depending on your rate, and whatever time it is, you can predict what the concentration will fall to, okay? So the first thing here is zero order integrated rate law. So for your lab, you actually will build a rate law, and then we will actually use somehow the integrated rate law. We're gonna use a second part, then that one's gonna, we're gonna learn that next week. So next week we'll learn the second portion of your lab. It has to do with an equation. But let's go ahead and get this done first. So the equation is a to the power of t minus kt, k is rate constant, plus a naught. Now the good news is these equations are on your periodic table. It will tell you zero order. This looks like this. But on the periodic table, I think they put the A naught in the front and then minus KT. They just flip the position of these two. It's the same thing, okay? So let's explain to you what each term means. This term, A at time T. So it's concentration of A at time T. All right? And then this term here is my rate constant. So it's a little k. And that one is my time, t. Whatever time is. And then this one here, A naught here is it. You see how this is A at t, this is A at naught, this is A in the beginning. So this is initial concentration because time is 0. Okay, so basically zero order integrated rate law, you know somehow about the concentration at the time equals to the negative of the rate constant times whatever time it is plus the initial concentration. Okay, it's just basically taking the zero order integrating it. And then if you take a look at this being as y equals to mx plus b. Okay, your m is your negative k, x-axis will be in time, y-axis will be in A to whatever time, concentration of A, and B here is your intercept, your y-intercept here. So I'm going to draw out the picture and it looks like a graph. So we know the slope is negative, so you want to draw a picture that has a negative slope. So again, y-axis is A. I guess I need to zoom out a little bit. And then this is time. You want to make sure this to time here is consistent unit. Don't be doing one here is minutes, one is seconds, or like minutes and seconds, because this is constant, has time in it. It's really important to make sure your units are matching. Anyway, so negative slope, let's just draw a negative slope. Oops. It should have been a straight line. Pretend it's straight, my hand kind of moved. Anyway, that's yeah, it should be a straight line. Just draw a straight line on your book. This here, the slope is negative, so that's why it's negative here, right? And so basically on your slope, you can get your K, rate constant. And then at this point here, this point right here, this is A at time 0, because time is 0 right there. Okay, so that's what the graph would look like. Negative slope, A is at time 0 right here, and this is A versus T. Now the unit of your K for anything that's 0 order integrated rate law would be m to the power m s negative 1. Okay, that's 0 order. Now let's go to the first order. So first order integrated rate law, and the equation actually looks almost the same. The only thing extra is instead of just A and A here, it's ln A and ln A over there. Okay, so it's ln AT equals to minus KT plus ln A naught. This is literally the same thing, but there's an ln there. So then if you do y equals to mx plus b, you know that your y-axis, in this case, is ln A, and then your x-axis is time. And then your A naught, like right here, that term, wherever the line crosses, that one is your A naught, ln A naught. Okay, now your unit for K in this case is whatever time. If your time is in seconds, or seconds per second. So if it's a minute, it will be per minute. But basically to the power of -1 the time. Okay, so half-life formula is given for this guy as 0.693 over rate constant, or ln2 over the rate constant. So let's take a look at what we were doing here. We were talking about integrated rate laws, where it's the mathematical relationship where you can have concentrations of reactants versus the rate constant and then time. So you can calculate exactly at what time is what concentration. So we were talking about zero order. We talked about the graph here, and then we were on first order integrated rate law here. So first order integrated rate law we'll be working on a lot, because this is like all the nuclear decay reactions are all first order. So there's going to be a lot of first order problems here for us to work on. And you want to also remember the half-life for first order. It does not depend on the initial concentration, because look at the equation. There's no A in it. There's no A naught in it. But the other guys, the other half-lives have A naught in it. So it does, those depend on the initial concentration. So that's the thing that's unique about the half-life of first order. It's actually simpler. Okay, so keep that in mind. And we were saying how once you have y equals mx plus b, we drew a graph out. So the slope is negative. That's why we have a negative slope. And that was negative k is your slope right there. Okay, and then time is on x-axis, ln a is on y-axis, and then this here is your intercept, which is ln a naught. So I wanted to show you how they came up with this equation here. So all you do is basically know the concept about how, you know, half-life means the time it takes for something to halve its concentration. So I wanted to kind of draw that little graph here I showed on the picture last time. Let's take a look here, I'll draw it out. So basically, it's like a curve where you go from, like it just goes down like that. So let's say this is like 100%, and then I guess like right around here, that's halfway, right? So that's like, so if this is 1, this will be like 0.5, okay? So that drops from 1 to half, agree? So it fell down by half, and the time, so this is the time, whatever time here, maybe this is like whatever seconds, I don't know what it is, x seconds. That x here, the time it took from it to drop from 1 all the way down to half, that is your half-life. So that x here is half-life. So this distance in time here is half-life. Okay, so to show you how they came up with this formula here, so basically we can use the first order integrated rate law and plug in 1 as your A naught, right? And then we'll plug in half as at time t. And we'll call t the half-life time. So instead of just plain t, we'll call it half-life time, because it is the time for the half-life to happen. Okay, so I'm going to go ahead and plug this in here into this formula with these numbers. So you just go ln, okay, so we're going to put the half in here, and then minus k, and then the time. So k is just rate constant here, and notice the k is actually in the formula anyway. So, and then instead of just plain time, we know it's a time to take for it to go from 1 to half, so it's really the half time, half-life. And then plus ln of the initial, which is 1 right here. Okay, so we'll just, you know, use algebra here, rearrange it a little bit. So we'll say, so move, I'm going to go ahead and take k times half-life, and that side plus on both sides. So it's no longer on this side, now it's positive. And then subtract it and take ln 1 minus ln 0.5. Okay, so basically k times half-life is now ln, now if you think about it, is 1.0. If it's ln minus ln, you can just combine it. This is just algebra here into this. So something is 1 divided by 0.5. Doesn't that equal to 2? So that equals to ln2. And K and half-life is here. So that's how you see if you wanted to get half-life formula, it's ln2 over K. And then because you know that, if you wanted to look for K, you just put K over here. You can also say K equals to ln2 over half-life. So, you know, whatever you're looking for whenever you're doing calculations. So just know that this is linked together. And the reason why the 2 is there, or ln2 is about 0.693. So sometimes people just memorize this. But, you know, sometimes when you're like really stressed and you can't think straight, you know, just understanding how this works. So this is an example of basically plugging in values, and this gives us the formula here. But later on, we'll actually be doing problems to solve, maybe we'll solve for time, we'll solve for rate constant, we'll solve for something in the question using the formula right here, okay? So this is first order integrated rate law right there. Let's go ahead and take a look at second order integrated rate law. And just remember, all this information here it is compressed on a chart on slide number 22. But I do want it to, I just wanted to work it out so you know you have an example and it's not just some lines and numbers on a table. Okay, so let's take a look at second order. So second order integrated rate law. All right, so for the formula is 1 over a at time t equals to a positive slope of kt plus 1 over a at time naught, so time 0. So in this case, if you have y equals to mx plus b, now you have a positive slope. So the chart will look a little bit different. It's not going to have a negative slope, it will be a positive slope. So if you have a chart, a graph, it would be a positive slope, so we'll go this way instead of the other way. If you go the other way, it's negative slope. Okay, so 1 over a is your y-axis, and then of course this here is my intercept, so this one here is 1 over a at time 0. And of course my x-axis again is a form of time. Now a lot of times we use seconds, but just keep in mind they can use minutes, hours, years, days, you know, whatever time that will fit into whatever the problem is. So because sometimes the question, you know, they have a longer time frame, maybe they'll be using years, maybe they'll use hours, or if it's a short time, then maybe they're measuring by seconds. But you know, usually seconds is most common. Anyway, so we have this here, and if you had your k here, the unit for your k would be m to the minus 1, s to the minus 1. So if you see something like, you know, that had a k that this unit, it might be a giveaway that, hey, this is a second order if you didn't recognize. But usually because these equations here are given on a periodic table, it's kind of easy for you to remember which is first, second. It'll tell you 0 is this equation first, is this equation second, is this equation. Okay, so you'll be able to see it. All right, so let's try out a problem. Okay. So I'm going to work out a problem here. We're going to do a first order problem. Basically, just remember, if it says second order, use this formula. If it says 0 order, use the 0 order formula. So we're going to do first order one here, okay? So the decomposition, and I will say most of the questions on your quizzes and tests should be first order, but not all maybe. But first order will be most common, okay? Just because we're going to talk about decomposition reactions a lot, and they're all first order, especially nuclear decays. So the composition of SO2Cl2 is first order, it says that. And then rate constant. So rate constant is your little k, okay? Is 2.90 times 10 to the minus 4 per seconds. If the reaction is carried out at the same temperature and initial concentration of SO2Cl2 is 0.0225 molarity. What is the concentration of SO2Cl2 after 865 seconds? Let's see how many of us are here today. Let's see. And everyone who's here said good morning, right? Make sure you guys are, if you haven't, make sure you say hi in the chat so I know you're here. All right, great. So that way I can keep track of your attendance as well. All right. So this is first order. I'm going to go ahead and write down the first order equation for you. Now remember, this will be found on your periodic table. Although on your periodic table, they'll write the ln A naught first and then the KT afterwards, but I like to follow the y equals mx plus b format. Like that. This is y mx b. Okay? The periodic table didn't like the negative in the front, so they just put ln A naught minus KT. It's the same thing, okay? But I just like it set up like that. Anyway, so we'll have AT. Do we know what we're looking for? We're looking for what is the concentration of this thing after 865 seconds. So we're actually looking for A at time 865 seconds, okay? So our time is 865 seconds. And they gave us the rate constant, which is in units per seconds. So seconds here and per seconds, that's great. You want to make sure your K and T unit match up. We're looking for this. Do we know our initial concentration? Yes, it says here initial is 0.0225 molarity. So all you do is you plug in the values. Now, the biggest problem here is number one, sometimes you mix up your units. Sometimes if this is in minutes and seconds and you don't keep it consistent, you can't multiply minutes and seconds and think it's the same unit of time. It's different. You have to convert it so it's all one unit of time. Keep it seconds, minutes, whatever it is, just one unit, okay? And then we're solving for this guy. So sometimes they plug in the wrong value. They put this one over here when it's not supposed to be. It's supposed to be this guy here. So just knowing what the terms mean is important, okay? So we're gonna look for ln A at time t, which is, we know it's 865 seconds, okay? So our time t is 865. Plug that in here. Now it's negative k. Do we have a value for k? We do. Rate constant is 2.90. Sorry, I ran out of space. It's gonna write a little bit small. Times 10 to the minus 4 per second. Hopefully you have more space than I did. Plus ln A naught, and A naught was this, so I'm just gonna go ahead and put that in, 0.0225. And that's in molarity, so just know that when you calculate your A here, it will be in units of molarity as well, okay? So seconds and seconds, that's good. So that way you know per seconds times seconds, it cancels off essentially. You don't wanna do a minute and a second, multiply them together, then you'll be in trouble. So let's go ahead and solve for it. Put this in your calculator, see what you guys get for this term here. So that equals to ln A at time t, which is 865 seconds. So that's what we're looking for. What do you guys get for this term over here? So I'm going to try to do that together with you. So it's ln 0.0225. And then minus k, so 2.9, 10 to the minus 4. Actually, let's put a big bracket here. Times 865. I got negative 4.04. Okay, 4.045, blah, blah, blah. It depends like if you rounded anything or kept it straight through. 4.0450, blah, 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 it keeps going. 4.045, we'll write down whatever that is. I never round, I keep the answer in my calculator. Like I'm not gonna like click this away, I keep this in here, okay? And then how do you get rid of the ln? Okay, so when you do this, you have ln, you take e on both sides, okay? So you get rid of this, and then you have at is literally e to the power of negative 4.045, whatever the number that we had here. Okay, so take e to the power of that, see what you guys get. I got 0. Yeah, without the m, since we know the unit is going to be m here, this at is going to be m. So 0.0175. Okay, hopefully you guys got that. Now this will be in molarity. So I just took e to the power of my answer. But you know, everyone's calculator is different, so you want to make sure you are using the calculator that is allowed for your test, and you practice using it so you know how to use it when it comes to test time. All right, so let me know. Hopefully you guys are okay with this. We all know how to use our calculators. Now I want to go ahead and do some more problems. We are going to try more versions. We're gonna have some with half-life in it and different kinds of decay questions. So I'm gonna go ahead and change to the next question, okay? Hopefully you guys all got this written down. All right, the next question I wanna work on is this one. So it says the first order reaction of SO2Cl2 converting to SO2 plus Cl2 has a half-life of 8.75 hours at 593 Kelvin. How many hours will it take for the concentration to fall to 16.5% of its initial value? So since it says first order, I'm going to go ahead and write down the first order equation. ln AT equals to minus KT plus ln A naught. All right, and they also gave us a half-life. So I'm going to go ahead and write down the half-life formula. Half-life formula was ln2 over K. All right, so let's take a look here. And then K equals to ln2 over half-life. Same thing, right? That's the formula we knew. So let's take a look at this here. It says, how many hours will it take for the concentration to fall to 16.5 of its initial value? So a lot of times, this is like basically an example test question. You'll see something like this on your quiz, your test, it's possible. But it says here, how long will it take for it to drop to 16.5 of its initial value? And you're like, there's really no real number given. There's no actual concentration values given. Agree? There's nothing, and you're like, most people get stuck and you don't really know where to start. But if it says it falls to 16.5% of its initial, what do you always start at? If you're talking percentage-wise, where is your starting point? You start at 100%. They don't spell it out here, but when there's percentage, you always start at 100%. So your initial would be 100% right here. Okay, and it says falling to 16.5. That means how long will it take? So how much time, what's the t, for you to go to 16.5 of your initial, that's 100. Okay, so that's where you're gonna put in numbers. So the next question after this, we'll do something that's worded a little bit different, and you just have to remember you have to read the questions carefully. LNAT is concentration at that particular time. So they're saying, what time will it be before it falls to 16.5%, right? Because it says 16.5 off its initial. So I'm going to go ahead and put 16.5 here. And then I'm going to put 100 right here. Okay. And then we have to put in T is what we're looking for. We don't know what the time is. And they did say the time will be in hours. So we want to make sure our K here, negative K, whatever we plug in, it should be in hours as well. Okay? Because they ask for how many hours. If this is in hours, this will be hours inverse. So good thing up here, that is hours. So that's good. But that's not K. What is this? This is half-life. So then you have to use this formula right here. If you want to find K, you take ln2 over the half-life, and we'll put it right there. Okay? So let's go ahead and do that. So it's ln2 over 8.75 hours. That goes right there. Okay? Now, before we continue with the math here, I want to tell you the most common mistake people do on this question. They don't tell you this. This is not on your test. They don't mention this. Okay? Although the equation might be on there. Actually, the equation is not on there. But they do give you this on the periodic table. Most common mistake. They take this, K, you see how this is temperature? They plug in here as the K because it looks similar. It's very familiar, but don't do that. This has absolutely nothing to do with the equation at all. It just tells you the temperature. The reason why they say this is temperature, because at different temperatures, it's different rates. You know, the hotter it is, the faster things will go. That's in general. So that here is just an indicator. It's really a distraction. A lot of times we'll plug this into here and they put the 8.75 in here and you're like, hold on a second, what am I solving for again? And they get completely confused. Okay, so it is very easy to get confused by it. So I wanted to kind of make sure when you do this problem again later today, just rewrite it and remember, write down this formula, know what each value means, and plug it in accordingly. Don't just put in whatever is convenient because they're always there to distract you, okay? So let's go ahead and solve for t here. So what you want to do is you can go ahead and use your calculator and solve for t. I can rearrange it a little bit to make it a little simpler. So I'm going to go ahead and do the whole positive side here. So ln2 divided by 8.75 hours here times t is on this side. And then I'll do ln 100 minus ln 16.5. And then t is basically this term divided by this term. And you can use it on your calculator and just go with the calculation, but I can write it out so I can show you. So this you can do ln 100 over 16.5. You didn't need to do all of this. You can just plug all these are all numbers. So if you're scared of natural log, just punch it in your calculator, turn them into numbers, and then just write it down and try not to round too much. But if you do round, the answer will be still close enough because it's multiple choice, you'll still be able to figure it out, okay? So this divided by that term, so ln2 over 8.75 right here. And then your answer will be in hours. Okay, so let's see what you guys get here. So it's like a matter of like, do you know how to use your calculator? It's very important. You have a calculator, are you comfortable with using it, punching in formulas? Hopefully you guys also end up with the same answer. So I'm gonna go ahead and try doing it and see. Let's see. We want to do 100 divided by 16.5. Get about 20, well, if we keep 3 sec fixed, it's 22.7, but it's this is what I get on my calculator, 22.745, blah, 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 okay? So about 22.745, perfect. So that's great. So that's what you're supposed to get, all right? So just want to make sure you guys are comfortable with using your calculator. Now, so this one here, the question said following to 16.5, so you put 16.5 here. Now I want to give you another question where it's going to be worded a little bit different, okay? So here's two versions. So I'm going to split it to part A and part B. So let's go ahead and write that question out. So this is part A. It says here carbon 14 has a half-life of 5720 years. This is a first order reaction. So this is like carbon dating stuff, okay? Now, if a piece of wood has converted 25% of carbon 14, how old is it? Okay, so it's first order. I'm going to go ahead and write down the equation for you for first order, okay? But just remember, the equations are on your periodic table, so you will be able to find it. But when you do your homework, you're going to do these formulas. So often first, zero, second order, you're going to accidentally memorize it. The second is 1 over, and then the 0 is just a regular A. So this is the only one that has a log in it. All right, so we have this. Now let's take a look at the question once you guys are done writing this question. Notice it is worded a little bit different from the first question. This question says, here's the half-life. It's first order. The wood has converted 25% of carbon 14. So basically, 25% of carbon 14 is now gone, converted over to the other form of carbon, okay? So this one here, it says, how many hours will it take for it to go to 16.5? This is going from 100 to 16 and a half, right? What is this going from? They say they switched over 25% of it. How much is left over if you converted 25% of it? You have 75% left over. And what goes in here? Do you put 25 or 75 here? They're saying this is concentration at the time of. Converting away 25% does not mean 25 goes in here. It means you still have 75 left over. 75 goes here. Okay, so you see how the question just changed it, like the numbers, like earlier, this one here, you just wrote the number straight in. So this one here, you can't write the number straight in because it's saying you converted 25% of it. What's left over? You have to put what's at that time in here. Okay, so this one here, that's the common problem. People put 25 in here and get it all wrong. Okay, so what you want to do is know that it starts at 100, converts 25% away, so what's left over is 75. So let's put 75 right here. Okay, and it says how old is it? So they're asking for time. So we need to put K somehow in here, and we are looking for T. This is what we're looking for. How old is it? Okay, and I imagine it's going to be in years because our half-life is in terms of years here. But let's go ahead and put in ln. Where do you start off? If they don't tell you an actual number, if they give you percentages, your original is always 100%. Okay, so I just wanted to make sure you don't always just write a number in. Sometimes you write the number in, sometimes you do the subtraction. Okay, so just read the questions carefully. All right, so let's take a look at this. So again, you need your K, we're looking for T. How do you get K? They gave you half-life. That's what you want to go for, okay? So half-life is 5720. So what was the formula for K again? K is ln 2 over half-life. Okay, so let's put that in. So ln 75 goes here, minus ln 2 over that 5720 years. So that's my K. We're looking for t plus ln 100. Okay, so you can go ahead again and solve it on your calculator. I'm going to go ahead and try to like rearrange it algebraically, but you really don't. I mean, if you can do it in your head, you can go for it, okay? ln 2 over 5,720 years times t, ln 100 minus ln 75. And when you do this, your time comes out in years because this is in years over here, all right? So you want to make sure, you know, the t here always match with the unit of the time. Like if it's years, your answer will be years. If it's hours, it'll be in hours, minutes, just whatever it pairs with here. And if they ever give you two different units for these two terms, you just convert one of them to match the other, okay? Now let's see what you guys get here. You know, with some rounding here and there, you might get different answers, but it should be pretty close to, let's see. Okay. Around 2374, 2375. Pretty big number. If you don't round at all, this is what you get. Okay, so just make sure you are putting your brackets in wherever you need it, okay? That's the trick about, you know, with your calculator here, just making sure you know how to put in these calculations here. You should aim to get something like 2374, okay? Any questions with the calculator here? Now, I'm going to go ahead and write the part B to this question here, okay? And it's right here, part B. If a piece of wood has converted 75% of carbon 14, how old is it? So they convert at 75 this time. Now what do you do? Well, a lot of people say, well, just put 25 here and keep everything the same, okay? So you could do that. Now I want to show you a shortcut, okay? But this shortcut only applies to first order and exactly at half-life times. So I want to take a look at this chart again. While you guys are still writing, give you guys a little bit of time. We're going to look at slide number 21, okay? Right here. Zoom in a little bit. So if you look here, because it's first order, the half-life stays the same, the time here, because it's independent of the initial concentration. So anyway, this is one half-life. That's another half-life because that's the time it takes from going from 0.5 to 0.25. That's half of it. What's half of 0.25? 0.125. That's another time. So each time you half it. So what are the points that you stop at? So I'm going to go ahead and write in percentage-wise, okay? So if you start off at 100, what's, oh, I gotta zoom out. Can't see my page. If you start off as 100, your next stop is 50, agree? 50%. And then the next stop, you go to 25%, agree? And then the next stop, you go to 12.5, and you can keep going forever, but just have it every time, okay? But each time you take from one to this half, from this to another half, this is your half-life right here. Agree? So lucky for us, we are trying to find Because it converted 75%, it is now have 25% left over. So they're asking, how much time does it take for you to go from 100% to 25%? So you could have done, put 25 here, put all this in here, and then you can solve for your t, right? And the t that you get will be the same answer as 2 half-lives, because this is 1 half-life, this is the second half-life. Agree? And how much is each half-life? So we just know that there's this 2 half-life. So it's 2 times 5, 7, 20 in years. So this is a shortcut. Okay, now you can only use it when you have 50, 25, 12 and a half, perfect numbers. You can't say, oh, well, what if I do 75? Can I find something at 75? Just, take this one and half the time. Why can't I do that? People try to do that, but you can't. You know why? Because this is not a straight line. If it was a straight line, you could have done that, but it's curving. So you can't just say, oh, I'm going to put in the middle of that and just half it. You can't just do that. So that's why when you calculated the time for at 75%, it's 2374. It's not half of 5720. You see that? But just it's a common temptation. But if you saw something like this, yes, you can go ahead and just do that. You could have done that because this is exactly 25. That's 2 half-lives. Okay, so 2 half-lives would be what? 11. 440. Okay, that's one way. Alternate method is go ahead and plug the same equation here, and all you do is switch from this 75 to 25 because it has converted 75% of that. You'll get the same answer, okay? Well, close enough. Sometimes with rounding, it'll change a little bit, but it'll be around this answer right here. All right, so that is, half-life and stuff. So I'm gonna go ahead and ask you another question on half-life here, based on something like this. This is an easy one, okay? It says here, now you will get half-life questions on your tests and stuff. So this would be like your easy part. A is turning itself to products, and your half-life is given as 150 seconds. This is first order. What percent of sample remains unreacted? So that means unchanged, right? What sample remains unreacted? How much of A is still there after 450 seconds? So you could have said, well, I know time is 450. My half-life is given here. I can change it to K. I can use my first order integrated rate law. You could do that, right? Just plug the numbers in. Like, start at 100% and then look for A at time T, and your T here is 450 seconds. Plug this in for your half-life. So you can use the same equation. But because 450 seconds is such a perfect number, it's a multiple of 150. You see that? Then you can use your shortcut. So it's only when it fits perfectly that you can use your shortcut. Otherwise, you need to use your integrated rate law. Okay? So how can I see? Because I know that 150 times 2 is 300, times 3 is 450. If you knew that, you can skip the integrated rate law equation. Otherwise, you can still solve it using integrated rate law equation, but obviously this one is faster. 100% goes to 50%, goes to 25%. Remember we were doing this? And then goes to 12.5%, and then you can keep going. But this is 150 seconds. This is another 150 seconds. This is another 150 seconds. And that total here is 450 seconds. You see that? So, well, that's your answer. 12.5 sample remains unreacted. Now, if they ask you how much of it has converted over to products, then you will just basically say the answer is 100 minus 12.5. So it really depends on what the question is asking. If they ask, remains, how much sample remains is this one. How much of it converted over is 87.5. So you got to read the questions carefully. And sometimes, remember, when it's perfectly matching numbers at exact half-lives, you can use your shortcut. Otherwise, stick to your integrated rate laws. Okay? So I'm going to write another question here. This one here will require us to use our integrated rate law twice. So here's an example. In the first order reaction of Y going to Z, Y is 0.0400 molarity initially. And Y equals to 0.250 molarity after 15 minutes. What will Y be after 175 minutes? All right, I'll let you guys write this. Let me see if I can run a poll for today. If you guys got ideas for polls, let me know. I'm gonna go check what polls I have available today. Oh, my computer is really acting crazy. I'm making sure I shut down things that I don't need. No, right here. All right. Let's do hobbies today. What are some of your hobbies? Launch poll. You can pick whatever, and if it's not listed, tell us on chat. Let's see. A lot of us like reading. Actually, it's pretty music and movies and sleeping. Sleep is good. Digital art, baking, that's cool. Those are cool. I don't know how to do digital art. Sleep is life. Yeah, sleep is good, you know. While you guys are young, you don't have to sleep that much, but sleep is pretty nice to have. Watching and playing sports, dancing, that's fun. Walking on a beach, that is so nice to be able to walk on a beach every morning. You are so lucky. Crafts and creative writing, that's awesome. I love that. So did everyone participate? Okay, play guitar, write music, that's awesome. Yeah, you guys are a bunch of talented people here. All kinds of cool stuff that you do. It seems like music, movies, TV are taking a front lead right now. Did everyone vote yet? Again, we still have roller skating. That's fun. Yeah, I don't know how to skate at all. I guess maybe I should learn at some point. Ice skating, that's even cooler. All right, so let's see. Did everyone participate already? All right, I'm going to go ahead and end the polling. So let me read out the options here, I guess. What are some of your hobbies? You can pick multiple options. We have reading, enjoying nature, give us examples, sleeping. I have no time for hobbies. It's because you work like 5 jobs and you have like 10 classes. Music, movies, /TV, something else not listed here, working out, does this count as a hobby? Sometimes it's just self-care. All right, so I'm gonna go ahead and end polling, share our results real quick. Music and movies took the front lead, and obviously you guys have a lot of other stuff on here that's not listed. So that's pretty cool. All right, so I'm gonna go ahead and stop this, and we wanna go back to our math. Back to our math. So ice skate. Yeah, is there a place to ice skate in Florida still? Do they have like ice? Well, I guess, if you go to where the ice hockey plays, they have a skating rink there. Countryside Mall does, really? I had no idea. That's cool. That's funny. I had no idea that it does. That tells you how often I go to the mall. I've actually been there maybe twice. That's pretty cool. Yeah, so you guys can go explore it, go try ice skating. All right, so let's go back and try to work on this problem here. So this one's a little bit more challenging, maybe. It's not really that too much that bad. So I just wanted to show you, it's worded differently here. It says this is first order. Here's my reactant. At first, I have 0.04 molarity. And then after 15 minutes, it came down to 0.25 molarity. What will Y be? What will my reactant concentration be after 175 minutes? So instead of flat out telling you the half-life or flat out telling you the rate constant, what they did was they give you one set of information here. So you can process the rate constant here, so you can use it again in the question for 175 minutes. So that's what I'm saying, like you have to like do your integrated rate law twice here. So that's a straightforward way to do it. So I would say, well, let's take a look at the first scenario here and find out what my rate constant is, and then I'll plug in the rate constant in for the second time here, okay? And my initial will stay the same. We'll start the initial at 0.04 again for the second time. So let's go ahead and write the equation down. Ln AT equals to minus KT plus Ln A naught. Let's go ahead and plug it in. This one's 0.25, so Ln 0.250 at time t, which is at 15 minutes. I'll go ahead and write 15 here. I don't know why my pen is like being weird today. And then minus k, I don't know what k is. Time is 15. Okay, I have to change pen. It's like dying. 15 minutes. So that's why I wrote the 15 here, because later we'll have a 175, so you can differentiate it. Usually I just leave it as t, because this is your t. But we have two t's here in this case. So Ln 0.04. Okay? So basically we can solve for k here. I'll rewrite it. K times 15 minutes is Ln 0.04 minus Ln 0.250. That's K times 15 minutes. So K would be Ln 0.04 divided by 0.0250 divided by 15 minutes. Okay, or you can just plug it in your calculator, get a number, but I like to do this and then keep that number on my calculator. But it ends up being like 3.133 10 to the minus 2. Let's see, something like that. You know what? This is not 0.04 here. What's wrong with me? The number can't get bigger. Why didn't you guys catch this?
I was gonna say something, but I was like, I don't
know. You can't get a small number to get bigger. It's supposed to decompose. Come on, guys. I'm the one that's not awake, but you should be awake. There's like so many of you to catch my mistakes. Anyway, it's supposed to get smaller, okay? So yeah, I was like, hold on a second. Why is it getting bigger? All right, let's do that. 0.4 divided by 0.25. Yeah, 3.13335575. But you know, you just write that down and keep the number on your calculator, okay? Because we'll use it on the second part. So once you find a k, you're like, oh, so this is what we were supposed to do. You know how the question sometimes gives you the k and sometimes it gives you the half-life to get the k. But anyway, that's that. So now we set up, what will the y be after 175 minutes? So then you go, okay, I found the k. Now I can set up my next thing I'm supposed to solve for. I'm supposed to solve for my A at time 175, the new time, equals to minus k. So I'm going to go ahead and just write this term in here because I'm not going to round it. Okay, anyway, I'm just going to write k and know that the k goes here, okay? And this is what I have on my calculator. All right, so we got this, k, and then t is 175 minutes. So before we get here, can you tell me, is your answer going to be less than 0.225 or bigger than 0.25? It should be a lot smaller because 15 minutes, it went down to 0.25. After 175 minutes, it will be smaller than 0.25. Okay, just kind of like gear yourself up. So if you do like make a math mistake when you're typing in your calculator, you can catch yourself in case it comes up with a different number than expected. 175 goes in there plus my ln 0.4. Okay, so we got that. And so we are looking for this term here. So basically just plug this in and solve for it, okay? So whatever your k is, put it together with negative k, 175, and then plus ln 0.4. On this side, you should get to be about negative 6.39. And all of this together, okay? So I got my k here, negative of that, times 175. And then I have to add that plus that number, ln 0.4, and then we get negative, this is what I have, 63996. It's really 6.4, but something like that. So 9967, something like that. But okay, how do you change that? This is now ln A at time t that we're looking for, right? This is ln t time t, which is 175. So to get rid of the ln, we take e on both sides. The last one with the formula shows with 0.2. Oh yeah, let's erase that. Thank you. It's 0.25 and 0.4. I don't know why I got my extra zeros in there. So we got that away. So now A at time 175 equals to, let's see what you guys get, e to the power of that number. 1.662 10 to the minus 3. So we are at 366 here. Yeah, it looks like it. So 1.66 times 10 to the minus 3. And this will be in molarity because the question started off in molarity. All right, so we did a lot of examples here. When you do your dynamic study modules, homework quizzes, you'll see more variety of this, okay? So you do have to practice because this is gonna be, you know, I guess it's kind of new stuff, but it's really not that hard once you practice a lot. Where did the 6.39967 come from? When you put the k, negative k, which is that term, times 175, and then you add ln 0.4. That's the answer right here. Like I basically just work this, and that equals to this, okay? You can't get that? Okay, so let me show you how I would do on my calculator. So did you get this here? Yeah, you have to get negative. You have to take that and turn it into a negative first. So all I did was, okay, let me start over. So get that part again. So to get that, I literally just put in, everyone's calculator is a little different. So you might be doing yours different. I like to do it stepwise. So I like to do 0.4 minus, divide by 0.25. That was the ratio there. So once I know the ratio, I take natural log of that. And then I want to divide it by 15. So that's how I got this. See that? Now once I got this, I put it right here and I take a negative of that. So again, my calculator is very different from yours. So now I have a negative of that. That's my negative k right there. and then that times 175. And then I have to add ln of, what's it, 0.4? Yeah. That's what I got. Okay, but it's all just using your calculator. I just want you guys to practice doing this till you're comfortable, because during your test, you don't want to be like, how am I supposed to put this on my calculator again? You can't figure it out. And like, you don't want that to be a reason you don't do well. Okay, so this is a time to practice. It's funny because now we're like, this is how you use your calculator. So yay, okay. Hopefully that helps. Now if you keep practicing, it's just a matter of like putting brackets in where you need to, learning how to use your calculator, because everyone's calculator is a little different. If you like told me to use someone else's calculator, I might cry, like, because I'm so attached to mine. This calculator is older than you guys. I am not lying. It is older than you guys. This calculator is, how old is it? Over 20 years old. And some of you are not 20 yet. Some of you are still teenagers. So how old is it? I got it in 1990. I think I got it in 1996. No, 97, something like that. Some of you might be like, I wasn't born yet. But anyway, like that's how long it's been with me. And I kept this because this is the one I know how to use. Okay, so make sure you guys get familiar with the calculator as well. Like, yeah, don't take my calculator from me. I'm really attached to it. You don't have to be as attached to yours, but you want to be comfortable with it. Okay, so hopefully we all know how to use our calculator for this. Now, we've been talking about rate constant a lot, so I want to talk a little bit about what that K represents and how our rate constant can change. Okay, so this is basically Arena's equation right here on slide number 25. Basically how like the K is affected by a few different things here. So I'm going to go ahead and write it out. Basically this is what we're going to work on. This is Arena's equation. I'll write out what each term means. Let's go ahead and write that out. But this is the equation I'm trying to work on, is K rate constant equals to A, some term here. What is A? And then e to the power of EA over RT, or negative EA. What's EA here? That's activation energy. So I'm going to go ahead and write it out and explain each term out separately so you have it in your notes as well. Okay, so this is what we want to do here. Yeah, and basically a form of this equation is in your part, is it part C of your lab, where they tell you to graph it. I'll show you how that's derived from this equation in a little bit, but let's talk about this real quick. We can talk about it on Wednesday too when we get to it. But basically, this is A, E times E, and then to the power of negative EA, which is activation energy, over RT. So basically it's two terms, okay? So this is my rate constant here. So it just tells us, the bigger the rate constant, the faster my rate will be. So, earlier when we first introduced the K, someone asked, is the K always going to be a big number? Well, not necessarily. It can be a small number if it's a slow reaction. It can be a fast number if it's a quick reaction. So it really depends. Now, so what does the K, where does it come from? What does it depend on? It depends on, obviously, these terms here. So it's A here. We call A here the frequency factor, okay? And then this big term here, we call this the exponential factor. So in general, the frequency factor says how often is there an attempt to do a reaction to make my reactant to turn into product? Like how often do they try to do it? So basically, do they collide? And did they collide at the right energy level? Did they collide at the right orientation? That's like how they attempt to do the reaction, okay? The molecules have to meet. So under frequency factor, it depends on the collision frequency. So the more collisions happen, the higher chance of a reaction actually trying to take place. That would, increase the rate constant somehow, but that's in a term right here, basically. And then part B here, it says orientation factor. So, like if you're trying to react, the certain end of the molecule and the other end collide, well, nothing's going to happen because you're not reacting, you're not touching the right molecules to each other. So that's important, orientation factor, okay? So that's how often something tries to do the reaction. And this term here tells you how many of them actually pass through and successfully complete the reaction, the percentage of it basically. So it is actually a number between 0 and 1. A number, because it's a factor, it's going to be between 0 and 1. Because like 0 is everybody failed, 1 is everybody went through, right? 1 is 100% basically. Okay, so under here, this is e to the power of EA over RT. So what's EA here? This guy here, negative EA, that's your activation energy. So you guys heard of activation energy before? So we'll talk about what activation energy means. And basically, we will be using a form of this formula, just rearranged into y equals mx plus b in your lab, and we will be calculating the activation energy for your experiment in that, okay? So that's why you'll see a form of this equation on your lab. That's activation energy. And then we'll talk about this in a second, but this R here, that's your gas constant. Again, gas constant. So over here, this gas constant here is, since we're talking energy here, our gas constant that we use with this term, we have two forms of gas constant with different units. But the one you can use here is 8.314, which is what you will be using on your lab as well. 8.314 joules per moles Kelvin. Those are your units, okay? The other one is 0.08206 liter ATM moles per Kelvin. The reason why there's a connection because ATM liter is like to joules, there's a conversion. It's like about 101 or 110, something like that. Okay, so this is 8.314 because we converted ATM liter to joules here. The number changed a little bit. All right, but it's still the same gas constant that you know. And then T here is going to be your temperature. Now, because we are using our gas constant, our temperature must be in unit Kelvin. You see how there's Kelvin here? Our activation energy will be in units joules. Our temperature will be in Kelvin. Okay, so just keep that in mind when we're doing calculations, but this is what that means. So going back to the factors here, we say this is how often they try to do a collision, and if they collide a lot of times and they collide with the correct molecules touching each other, they will have, some attempt on the reaction. But it's not just the frequency because, not everybody who tries to do the reaction will pass through. Only some of them will. And what does it depend on? It depends on the activation energy and your temperature of your reaction. Okay, so let's talk about, well, we know that temperature, the hotter it is, the more energetic things get. So that's something we already know. But let's talk about activation energy, okay? So here's a picture of activation energy right here. On a chart, if you're trying to make reactants turn to product, there's a little process before it goes from here straight down to here. It has to go through a hump before it comes down here. So this here, from where you originally start, where your reactants are, or where you, sometimes it's a reverse reaction. So this is a forward reaction going from H2, O2, 2H2, and O2 to 2 waters, okay? So the activation energy is from this line here to the top of the hump. So this is the blue arrow. Now, if you were doing a reverse reaction, trying to make 2 waters break down into hydrogen gas and oxygen gas, what's your activation energy? It would start from somewhere below here, like somewhere here, all the way to the top. You see how much bigger that arrow will be? So, reactions like this, you see how this can go forward and go backwards because it's reversible. So the forward reaction activation energy is a lot smaller in this case than the reverse reaction activation energy. So just keep that in mind. So it's basically from the bottom of where you start to the top of the hump, okay? So a really, really easy analogy here is let's say this is our class, and to get an A in our class, obviously we know the rules. You have to take, you have to do well on your test and your homework, all your points add up, you get 90%, you get an A, right? But let's say we make it like something super simple, okay? So maybe we can say, for you to make an A in this class, all you have to do is be able to jump as high as 1 foot. How high is 1 foot? Like 12 inches, right? That's not very high. Can everyone jump that high? You guys can, right? Well, hopefully you can. So if you can jump that high, you got an A. So if that was my requirement to make an A in this class, do you think 100% of us will make an A in this class? It will be, because it's super easy. It's a small, easy activation energy to overcome, a very small barrier. What if I made it super, super hard? Like instead of jumping 1 foot, you have to jump 10 foot high without any assistance of anything. You're just supposed to be able to jump like, well, I don't have wings, so I can't jump that high. Some of you, maybe you can, I don't know. Some of you are super athletic. So in that case here, I might not even be able to get an A in this class because I can't jump that high. So it's basically the higher the barrier, the harder it is to cross over, okay? So activation energy therefore affects this part here, right? How many of them pass through. The higher the activation energy, the less of them will pass through. But if you have a high temperature, more of them can pass through because they have more energy to jump up against that barrier. Okay, and then frequency here says, this is how many times we attempt. Out of that, what's the percentage that actually passes through? So that's basically our activation energy. Now, why is it that we have that big hump? Why is it that we have that big hump? It's because when, for example, if you have a reaction, this is slide number 29 here. If you have a reaction trying to do a turn from N and C and flipping it back to C and N, you literally have to twist the position. You see how the blue is on the inside? You want the blue to go on the outside. How can you get from the inside to the outside? Well, you have to twist it. So you get to this weird position where it's twisted in the process of flipping over. This part here is so unstable. It's so unstable. So something that's unstable has high energy. Something that's stable is low energy, right? So because this is unstable, it's a very awkward position. The energy level is up here. So we call this awkward position the activated complex or the transition state, okay? So the reactant is here, going to the product, and here's your activation energy. So just for fun here, is this an endo or exothermic process? Do you remember? Okay, so here's our little recap. This here reactant going down to product. Do you see how the arrow activation energy is coming down? This is going to be exothermic. Very good. Okay, because this is a negative sign. So these things here still come into play. You will have a whole chapter later in the semester on exo-endo stuff, plus stuff built on top of that. Okay, so just, don't forget the stuff we've learned. So I'm gonna go do a little recap. I'll draw it out on our notes for us, okay? So yes, that one is exothermic. So I wanted to do a reversible form so we can do like, both directions. So I'm gonna draw first example here. So let's draw a chart like what we saw. So this is our energy chart, some form of energy, and then, we want to go from the reactant to the product. So I'm going to go from R to P. So I'll call this R, we'll call this P, and we want to go from R going to P. Now R going to P, you have this where you go to the top of the hump. Okay? So from here, we can say, because the R had higher energy than the P, energy went down. Delta H is negative. I should write negative like a normal person. Hold on. Let me write it out. Because I sometimes write negative V. Maybe I shouldn't do that right off the bat. But here's negative term, right? So it's exothermic. Okay, that's stuff we learned from before. Now, if you have trouble remembering, I like to think about as like, if your bank account balance was high and then your bank account balance was low, what sign does your transaction show? It shows negative, right? So you know stuff is leaving your bank account, energy is leaving your account, it's exiting, so it's exothermic. Okay, that's one way to remember it. And if it goes up, it's endo because it's coming in like indoors. Okay, so that's one way to remember that from Chem 1. Now, for our R going to P, our activated complex is right here, super high energy here, the weird awkward position. It's right up there. So this, from here to here, this here will be my EA or my activation energy. Going from R to P. Now, what if we did a reversible reaction? We took the same picture. Now we want to go from P to R, okay? Draw the same picture, no promises. So this is R, this is P. Now I want to go the opposite direction. We want to go from P to R. All right, in this case here, P going up to R, you notice the delta H size stays the same, but now it's the same size because it's the same energy gap. You see how the distance is the same? So it tells you it's the same number, but the opposite sign. It's going to be a positive sign. So this is endothermic. Okay, now this reversible reaction here, your activation energy looks a little bit different now because it's all from P to the top of the hump. So I was trying to tell you earlier how, you know, sometimes reversible reactions, your activation energy will be different from if you start from the reverse side or you start from the original forward side. Okay, so just keep that in mind. This here is a bigger activation energy than the other direction. But it's the same reaction, it's just reversible, we just flipped it around. All right, so hopefully we all are following this. Now, I wanted to show you a form that relates to this for our lab. So the equation is basically on this slide number 34. This is what you will be doing in lab. You will see this equation here. They will make you graph ln K versus 1 over temperature because that's your Y and your X. And then your M here is negative activation energy over gas constant. And your B here will be ln A. It's pretty cool how they make you graph and from there you can find your activation energy.